Thank you very much for the introduction, and thanks to the organizers for giving us the opportunity to present our vaccine, which is called deltaFLU, and which is an influenza virus vaccine, a replication-deficient intranasal influenza virus vaccine. Below here you can see that a schematic drawing, what's the hallmark of the vaccine. So one hallmark of the vaccine is its intranasal application, and having the advantage to induce immunity and protection directly at the site of the entry of the viral pathogen, the upper respiratory tract. Second hallmark of the vaccine, it's replication deficient. This means you spray the vaccine or the virus, the attenuated virus, into the nose. It infects the epithelial cells in the nose, produces its antigens, but does not form viral progeny. So you don't have shedding, and therefore it can be considered as a safer or new generation of a live-attenuated approach. So besides the intranasal application, there are several unique features with this vaccine. So here you can see the differences to the conventional inactivated vaccines in dark green, and in light green the differences to the current live-attenuated vaccines. So we touched already the intranasal application. So besides having protection and immunity directly at the site of the entry of the viral pathogen, another obvious practical advantage is that you have a pain-free application and it's easy to administer. Second point listed here is its cross-reactivity. So we were able to induce antibodies which are not only active against the homologous strain, but also against the heterologous strain. So in other words, we're able to neutralize drift variants with the sera from the immunized volunteers. Local immunity is the third point. So obviously, so it's actually no big surprise. We get nasal IgA in the washings of the volunteers. So here, more an issue is to get the assay. So you have you wash the nose with a volume of 5 milliliters, and you can imagine that's not the most sensitive assay. But as I will show you later, we have here a significant increase also shown with the local IgA. Self-adjuvant effect is somehow associated with the major mechanism of the vaccine, so it's associated with the deletion of its interferon antagonist. So the lack of the interferon antagonist induces or provokes the induction of higher levels of interferon, and probably you know that interferon is known to induce strong mucosal and B and T cell mediated immune responses. We touched already the replication-deficient phenotype, and this has the advantage that if somebody is immunized, goes home to or met somebody who has an immune suppression, basically there's no danger that the virus is transmitted to somebody like that and becomes pathogenic in that. Second advantage is that since it does not replicate, the reversion to the wild type can be excluded. And finally, the potential reassortment with the wild type in the nose, which is drastically reduced in comparison to the conventional live-attenuated approach. Finally, we produce in Vero cells. So Vero cells, probably as you know, are produced or have been used for different types of vaccines for many years, and most of all these Vero cells are non-tumorigenic. And actually we worked very hard and were quite successful in order to obtain quite high titers in this Vero-based system. This slide shows somehow one of the basics for the whole approach, meaning that it provided the basis for modifying the genome of influenza virus in order to introduce mutations, in order to delete genes and so on. And secondly, it's important in order to make strains quite fast and in an efficient way. And below here you can see how this is working. So you transfect cDNAs of newly recommended HAs and NAs into Vero cells, which have previously been infected with a so-called helper virus. You can also name it master virus. You get, important here, the master virus has been adapted or has mutations which allow high growth in Vero cells. In addition to that, they have an elastase cleavage site in the hemagglutinin and a truncated NA for selection purposes. Yeah, so you then, in the transfected and previously infected cells, you get then in the supinate and the mixture of the helper virus and the vaccine virus. Due to the selection mechanisms, mostly of it is vaccine virus. In order to get rid of the rest of the helper virus, you add antiserum and you end up with the vaccine virus. So as I said, this is very fast. It takes around 10 days. Importantly, we use cDNAs instead of plasmids, which saves you a couple of days. And also importantly is this the helper system. You have, so you, in comparison to the conventional reverse genetic system, we have to get 12 or even 14 plasmids in one cells. Here, you don't have this problem. You just have to get 2 cDNAs in cells which basically are all infected by the helper virus. So it's not only fast, but it's also a highly efficient system. Yeah, and this system is not only fast and efficient, it was only somehow the basics for generating this gene, so we call it a tailor-made influenza virus vaccine generated by reverse genetics. We have deleted, for example, the NS1 gene, and by deletion of the NS1 gene, we have attenuated the virus and at the same time increased its immunogenicity. Similar thing happened with BB1F2, again, by deleting BB1F2, we attenuated the virus and increased its immunogenicity. We also were able to introduce a couple of mutations which allowed to increase the yield of the virus. So for example, in the M1 gene or also the polymerase genes BA, BB2, and BB1. And finally, we also were able to increase the immunogenicity by what we call HA gene preservation method. This slide shows the principle of the first deletion, or deletion of the NS1. So NS1 is an interferon antagonist. And left side, you can see that we basically deleted the gene by excising it from the NS gene segment, get then the delta NS1 virus, which provides very important properties to our deltaFLU vaccine. First, it makes the vaccine, or the vaccine virus, replication deficient, meaning it's becoming safe. And secondly, because the interferon antagonist is missing, so upon immunization, high levels of interferon are induced. There's no counteraction mechanism against that. And because high levels of interferon are present, this is the explanation why this virus is, despite it's highly attenuated, it's also highly immunogenic. Yeah, this is a similar thing, just in a different description. So we call this also this intrinsic induction of interferon self-adjuvant effect. Left side, you can see what happens in the wild-type virus infection. So wild-type infects the cells, has NS1, NS1 blocks interferon and also other cytokines. And because of that, a lot of progeny virus can be produced, which is virulent. And we have here suppressed and adaptive immunity. On the right side, you can see what happens in the absence of NS1. So again, the virus infects the cells. However, here NS1 is lacking, so interferon and cytokines cannot be blocked, which in turn block then the viral production, so we don't have the formation of progeny virus. Therefore, the virus is highly attenuated, and we have here enhanced and adaptive immunity. This slide illustrates the second deletion we have made, the BB1F2. So we got aware of that when there was a publication that BB1F2 is a pathogenicity factor, which was in 2006. However, at that time, we were concerned that by deletion of this BB1F2, this might affect the viral growth or also might decrease its immunogenicity. However, as illustrated here, shown in this figure here, the opposite happened. So on the left side, you can see that the growth was even slightly enhanced, so that the dark columns correspond here to the double deletion mutant. And on the right side, you can see the immunogenicity, left single and double immunization with the single deletion mutant, with the NS deletion mutant, right to the NS BB1F2 deletion mutant. And you can see with the single, after single immunization, we have an increase of the, in this case, it's an ELISA titer from 130 to more than 1,000. And after the double immunization increase from 1,000 to 4,000. So nice surprise, not only we further attenuated the virus, made it safer, but also the immunogenicity increased and also to some extent the growth of the virus. So in clinical trials we have performed so far phase 1 and phase 2 trials with the seasonal H1N1 strain. Actually, we used the New Caledonia and later on the Brisbane strain. A total of 96 volunteers were included. We have been able to show it's safe and immunogenic in humans, have induced local and systemic immune responses, and have been able to show that we induced cross-reactive antibodies. With the pandemic, we used H5N1 as a prototype. 72 people were involved in these trials. We were able to show it's safe and immunogenic. Here it's quite remarkable, particularly for a live-attenuated approach, where usually the majority of the immune response is here in the with secretory IgAs. We get here more than 70% seroconversion already after the first immunization. And again, we get local and systemic immunity. So far we have only performed trials with monovalent strain, monovalent H1 and H5. Currently, we are in progress with our first trivalent trial, including H1, H3, and B. It's a total of 80 people. This trial is currently in progress. So it's a phase 1/2 trial. So we had to do 18 volunteers in order to show also the B strain and the H3 strain are safe, so we have been able to show that. So we're currently moving on with the trial. We have here distribution of Vero to placebo of 1:1, and this is a low dose, and we plan to go on after this trial, presuming the safety profile is okay to go on with a high dose. Here just some data, for example, from the H5 trials. Left, you can see the placebo, no increase in the placebo. Then actually left side is the low dose, which usually we consider low dose below 7 and high dose above 7. So left is 6.8 logs. You can see in the vaccine group, we have a significant increase after the first immunization at day 29, which increased after the second immunization at day 57. Right side with 7.5 logs, no increase in the placebo. Here at day 29, and that's it's quite remarkable, in particular since it's a live-attenuated vaccine, you can see that 75% have an increase of 1 to 40 or higher, which obviously increased after the second immunization. Here are some data, some example from what we obtained with local IgA. As I said, it's quite difficult, so it's quite reasonable to assume that with an intranasal vaccine you get a local IgA. The difficulty is to measure it. However, we were able to validate this assay. We get a GMT increase of 2.5-fold, which was statistically significant. Yeah, finally, important feature of the whole thing is to have a production system where you get reasonable titers. So we worked quite hard on that because particular Vero cells somehow have the reputation that they don't support the growth of influenza virus too well. However, by adding a media supplement with the mutations in the polymerase genes, mutations in the M gene, and particularly the M gene was quite surprising because at that point, so B virus is even published not to grow in the absence of an NS1. So it grows around 10 to the 4, which is not really reasonable at all for vaccine production. And we, as you see here, B virus, we pushed it in the meantime to the titer of 10 to the 8.6. Message here is we get this with any strain, we get the titers between 10 to the 8 or 10 to the 8.7, assuming a dose around 7, that looks quite sufficient to have a quite huge number of doses per volume. In summary, this deltaFLU is unique in that it has a so-called self-adjuvant effect through the interferon induction. It has cross-reactive properties. Is able to induce mucosal immunity, grows to high yield in Vero cells. It's well tolerated. We don't have any shedding so far. We did not see any difference between the placebo and the vaccinees, although considering the numbers are still low. Yeah, and basic message is that through deletions and modifications in the genome of influenza virus, we were able to generate a replication-deficient, highly immunogenic strain which grows to high titers on Vero cells. Thank you very much for your attention.
Thank you very much for sticking to your time. Are there any questions from the audience? Yes, please.
Have you done head-to-head comparison against flu mist?
In a clinical trial?
Either in clinical trial or animal models?
Not with the same strain. So we have done comparison, but we were not able to do it with the same strains.
And the data? And what was the result? What were the results?
The results, yeah, I think considering it's historically, it induced higher titers. To flu mist, yes.
Are you willing to say how much higher?
It's strain dependent, no? So it's highly dependent on the strain.
I must say that your results with H5 are rather surprising because everybody else, I believe, has shown that you really need a potent adjuvant to see good immune responses after 2 doses and not after a single.
We were surprised by ourselves, particularly for a live-attenuated approach. Now, for example, a particular immune was hardly able to see anything, any response for H5 now. So we were quite surprised by this data, but it's probably, I didn't show you this in addition, so what we have also introduced, so what we noticed is important that you preserve the structure of the hemagglutinin. Because if you keep the structure of the hemagglutinin, we noticed that the nasal cells are getting infected much better, so maybe that might be the reason for that. So I didn't show you that, but that's what I meant under the HA gene preservation method.
So you're leaving the polybasic site in there?
No, it's not the polybasic site, but the general, usually if you isolate virus, either in MDCK cells, Vero cells, or eggs, you always get mutations, even just after isolation. So we found methods to avoid that because we noticed that it's very important. So it's probably not important for inactivated vaccine, but we noticed for live-attenuated vaccine that's very important because the frequency you infect nasal cells is like 1 to 10.
All right, we have to move on to the next speaker. Thank you very much.